great to be here. Excited to have such a great lineup, and I can join here as well. So I'm going to talk about this Reinventing Solana theme. So this year is actually a big year for this blockchain Solana, because we're going to change basically everything, pretty much. We're going to change the protocol, the consensus protocol, but we're also going to change other things. And we're going to talk about that. However, I'm like working for Solana and ETH at the same time, so that's nice. Let me also have a grand overview what Itai did with a little bit more of an industry perspective. Let me. I hope you saw some jokes there. Same thing as you, almost the same waves, I would say. A little bit different, but pretty much the same. Good. But I'm going to talk about Solana. And nobody really understands Solana, I would say. This is certainly true for myself. So before I joined the company, I was supposed to understand the protocol. I never understood the protocol. And so that's how I basically ended up working for them, I guess. So I'm going to show you the new protocol, okay? The one we have been implementing now, the one which will be live this year for sure. We're testing it right now, and this is much simpler. And it's a simplex variant, as we just heard. So in some sense, kind of the application of what we just heard. So basically, I'm going to cover two papers in my talk. The first one is so-called Alpenglow consensus paper. This is joint work with two of my former PhD students, actually. So the new research team at Anza, which is the engineering firm for Solana, kind of came up, we came up with this Alpenglow consensus, and I'm going to tell you how and how it works, basically. And the second part is the so-called Constellation protocol. This is also with the same people, plus Max Resnick, a resident New Yorker, who basically is one of the, I would say, maybe the main guy or one of the first guys who considered these multiple concurrent proposers architectures. And this is the Solana version of this, essentially. Both papers are in a very different position right now. So this one here has been voted upon by the stakeholders of Solana and got 99% approval rate. And as I said before, we're basically implementing it right now. It's already live on some testnet. So this is very nice. The second one is very different. I don't know if you can read this. Maybe if you cannot, it's even better. So this is kind of the reaction you got on the internet when we talk about Constellation. Okay, so people are very upset about this, and they will fight to the last, tooth to not make it happen. But I'm going to still explain it here because I think it still has many nice ideas inside. Yeah. Good. So let's start with Alpenglow. So this is sort of the, I think, even official motto of Solana. As we heard before, we tried to reduce latency, as Itai said it, but we also tried to increase bandwidth. We tried to have, in some sense, a very performant protocol. This is what sets us probably apart from Ethereum, which is, was there first with smart contracts, which maybe cares more about decentralization. We also care about decentralization more than this other protocol I mentioned before, but we also care about these things. So sorry there's a few maybe industry slides a little at the beginning, but it will get better. So for bandwidth, I would say this was always a strength for Solana. So this is a protocol they had which used erasure coding. So it always cared a lot about sending data around reliably very quickly, okay? So that's a so-called turbine protocol they have right now. And we're gonna replace this, but conventional protocols are in some sense not very good with bandwidth, I would say. The classic protocols in distributed computing didn't really care about it so much. The model was basically having few nodes only. Think of something like 10 nodes maybe. And then bandwidth was not such a big problem, right? But if you go to hundreds or thousands or hundreds of thousands of nodes, then of course having, for instance, a leader sending everything around is a big bottleneck, okay? So we don't want to have that. And same thing for gossip protocols, which may be the other classic alternative here. It's just not very good with using the bandwidth the way they should use it. I have DAG protocols here as well. They are much, much better regarding bandwidth. In some sense, that's the reason they were invented. As you can see, I didn't quite put them as, it's not as good as Solana's turbine. And I could probably defend it, but I probably will blush a little bit while doing that. But I would say maybe the main problem of DAG protocols that we're going to hear later about is that they sort of need a little bit of load balancing probably. So you have multiple proposers which kind of work together or propose transactions together, and you have to know where you send your transaction to. So if they're not well load balanced, maybe you don't use the bandwidth as much as you could. Whereas coding-based protocols like Turbine, they would do that almost naturally. And yeah, Alpenglow might be a bit better than Solana's Turbine, but not much better. Then, as we heard before, latency is also something we care a lot about. Here, maybe the left would be better, less latency is better. So Solana currently has a finality for blocks which is quite fast compared to some other protocols, like let's say Bitcoin, which would be in some other room over there. But it's still somewhat slow. And we try to make this better. And it has something, this is also for Solana, it has something called optimistic confirmation. So this is not what I would call finality. It's not that you can say this transaction for sure is now in the block. It's just saying, yeah, pretty much we think it should be in the block. It's kind of like Bitcoin having you see a block in Bitcoin, you see a transaction inside, you would say, well, the chance that you have a fork there is small, and we can assume that this is fine, right? Maybe even after 5 or 6 blocks in Bitcoin. So this will be much, much faster already for Solana. But somehow this is apples to oranges comparison here, because this is really what I mean by finality. Here is finality that you cannot undo a transaction anymore, whereas this is just hoping the transaction is final. Now with Alpenglow, we try to get something like 150 milliseconds, I would say, on average. Real finality, okay, so that we have a transaction and it's inside. So that's something we really care about. And I would say this is, apples to apples comparison, those two things there. And maybe also other protocols quickly. So there are some which are around 400 milliseconds, so we are still quite a bit faster. So this has a high variance here, and I'm going to explain this. With deltas, you cannot explain this, but we have a real protocol, worldwide protocol. And so this is, in some sense, depends where you are. Like when comparing to this, also, this might be an apples to apples comparison, but it's kind of like different apples. And the reason is that this very much depends on many, many things. For instance, it depends on the distribution of the nodes worldwide, right? So whether they are more clustered at the same place or at different places, that makes these protocols, look better or worse. Good. So we tried this, as I said before. So we're basically running Alpenglow right now. What we're mostly testing right now is to switch from the old protocol to the new protocol. We want to switch without turning off the protocol and turning it on again. We just want the seamless switch in some sense. And this is one of those things where you see there's the old finalization latency here in the order of some seconds, 12 or so seconds. And then it drops basically to 0 if you go for 150 milliseconds after that. Good. What else do we want? We want, of course, a secure protocol. We call it the 20+20 security that we're going to get. And what I mean by this is basically we want to have a tolerance for 20% Byzantines and, in addition, 20% crash failures. So now to have a protocol which is Byzantine fault tolerant is of course very important. And we have heard before that we could have a higher fault tolerance here. But in reality, crash fails are probably happening much more often, okay? So you want to have this for security, but you want to have this just for everyday security in some sense. So that's why we opted for this protocol. Also, as we heard before as well, this is of course building a lot on previous talk, with this just 20% Byzantine fault tolerance, we actually can have a faster protocol, right? So if we want 33% fault tolerance, then we need one more round. And we care about latency, as I showed you before. So that's our security model. And yeah, we want to keep it simple. Okay, so a simple protocol which works, which does the job, we want to have that. Good. Maybe quickly, maybe you have seen this meme. There's this meme president from Argentina, and he rips off the ministries here. And that's sort of what we do for Solana as well. So we actually, when we talked to the founder of Solana and we presented our protocol that he should implement, I put all the ingredients of Solana protocol on a whiteboard. And then I kind of said, and Solana is kind of famous right now for proof of history. We said, you know, all these things are gone. We don't need them anymore. And this one here is the turbine data distribution protocol that I mentioned before. This is one which we are going to replace as well with something simpler and maybe even a bit faster. It's called Roder. And as Itai mentioned before, you basically need these two ingredients for a good blockchain protocol. You need a consensus protocol and you need a data dissemination protocol. So this is our data dissemination protocol. And then we need something on the voting side. We looked at, you know, when we did this, maybe this is a bit a different, I would say, setup than a typical academic, right? When we built our protocol, we didn't need to invent something new, okay? So when you're a professor or a PhD student, you know, you're only gonna have success in some sense if you have something new. Whereas if you're a company, you can just look at the literature and steal all the best ideas you find, okay? So to some degree, we stole a lot, okay, or were inspired by a lot of things that were around at that time. In particular, the whole simplex line of work, which we felt was very simple, and you know, don't like the name so much because there's, in computer science, if you have named 10 protocols, then you probably wouldn't mention simplex protocol for linear programming. But okay, so now you have two simplex protocols. But apart from that, it's a simple protocol, so it makes sense. And I should also mention Banyan as an inspiration, which comes from the corner of Jan, who's going to speak, I think, also sometime this week. He's here somewhere over there. Yeah, so which had this idea that you can basically combine a fast protocol with few rounds with a different protocol which needs a bit more rounds at the same time. So I'm going to talk about this in a second. So these are the inspirations. And since we had the data distribution protocol Roder, this is the voting protocol, it's called Voder. Good, so the plan is to just show you these two things quickly, Roder and Voder. And it's basically, I mean, the Voder part will repeat some things Itai said. I'm going to present it very differently, just with pictures, so that you hopefully get the big picture again. But if you understand everything he said, then it's, you know, then it's just repetition. But let's start with Roder. So maybe quickly, this is from the testnet currently running Alpenglow. Just a video I took, but you can actually go to this web page when you search for Alpenglow and testnet. Then you find this. So you have a bunch of nodes, basically, which are distributed in the world, right? This is basically how it looks like even for the production of Alpenglow. So there's a bunch of nodes in North America. There's a lot of nodes actually in Europe. This is what the testnet has in common with the mainnet of Solana and also the mainnet of Ethereum, actually. A lot of nodes are actually in Europe. And there's some in Asia, but not many, okay? Some in South America, some in Africa, but there's very few in the mainnet. In the mainnet, we have about 1,000 nodes. Here we have about 100 nodes, which basically take turns proposing blocks and making consensus about these blocks. But think about having 1,000 nodes which are you know, taking turns to propose blocks and have consensus on them. So let's look at the data dissemination. So we have blocks that we propose, one after the other. The blocks are the basic ingredient for consensus, right? We make consensus after each block. But in reality, when we look at the blocks, then they're actually partitioned into what we call slices here, so that we can pipeline the data out all the time, okay? So when you're currently producing a block, what you're really doing is you produce slice after slice and you send them out as quickly as you can. The slices include the transactions that are currently proposed by the users. Now, to make it even more complicated, each slice is not just sent out as plain data, just bits and bytes basically, but we're going to encode the slice in so-called shreds. And a shred is just, each shred is basically a UDP packet, okay? It follows what networking people would call the MTU limit, that it just fits nicely into a packet of about 1500 bytes. And this is coded in the sense that you see here a slice was this size, but I just doubled it. You basically use erasure coding here, or some other form of coding, but we use erasure coding right now, so that if you receive half of those shreds, you can reconstruct the slice. So that's the idea here. So it makes it a bit more fault tolerant, actually makes it faster as well. So that's the idea of the shreds. So we have the blocks, but the blocks are really slices pipelined, and the slices are really just twice the number of shreds we need to send these things out, and every shred fits neatly into a data packet. So how does this look like? So here again I have the shreds. So we always have a current leader who produces the block, or the slices, if I may say so. And then the leader, well, it has to send this information to the 1,000 nodes in the network right now, but this will be a lot of data, right? So think of these shreds. In reality, we don't have 6, we have something like 64 shreds, 64 packets times 1,000 nodes, right? That's 64,000 packets, which is a lot of data. Yeah. And so we need something to make this fast, okay? And the idea here is to use so-called relays. These are just random nodes from the 1,000 nodes. The leader is currently a random node from the 1,000 nodes. It takes turns, basically. And the relays are also randomly chosen among those 1,000 nodes. And they would relay the information. So when the leader makes a slice and splits this slice into these 64 shreds, then it just sends one shred to each of those relay nodes, which are somewhere in the world. And then the relay nodes would send out the information to the 1,000 other nodes, okay? This doesn't take so much time. This is maybe with a fast internet connection, and maybe I should say Solana, wants nodes to have fast internet connections. This takes maybe 1 or 2 milliseconds to send a packet to 1,000 nodes, even if you do it very naively, just with a for loop. But if you did it, 64 times this, then it would be 64 times 2 milliseconds, which is a serious time. Yes.
How does these relays interact with fault tolerance?
Yes, they don't interact with fault tolerance at all. They really just forward whatever they get. They don't care about it. They, in some sense, we have this 2x over provision at this point. So instead of the 6, or in my picture here, we just need 3 of them at the destinations. So if one of them fails, or one of them is Byzantine, actually, we can check that at the receiver, and we can remove that information.
Got it. So every shred comes with a signature from the leader?
Yes.
Got it.
Yeah.
Okay.
Yeah.
I just have a quick question about the networking aspect of things. Yeah. Why not use RDMA? And why UDP?
No, I mean, we don't use UDP. I just set this to make it sound simple. So we have something called XDP. We have better. I would say the Solana people are very good at these low-level technology things. They do all these things. Yeah. I should also say, this is sending to all the nodes, but what we could also do is, and which actually is done right now even, we could use real network multicast as well, okay? So instead of the leader sending something to a relay and the relay sending to everybody, some people, let's say about 50% of the nodes in the Solana network right now, they're connected to something called the 00 network. And the 00 network gives them a real multicast. So the leader could just send this one shred just to the multicast, and then it would just be sent to everybody automatically. which is nice. The not so nice thing about this, then you kind of depend on this one company who does this service for you, which is bad centralization. So the idea is to do both, right? It's not much more overhead. You can send the shreds to the relays and they send to everybody. And at the same time, you can send slightly different coded shreds actually via multicast to everybody. And whatever sort of shreds you get, you can reconstruct the slice. That's the idea.
Right.
Yeah. There's one more.
Thank you. I want to know what's the degree of redundancy of that, because you are sending something that takes 32 packets, you're sending 64, every 64 are sending to all 5,000. So how is the degree of duplication here?
I mean, the replication is really a factor of 2. So with half of the shreds, you get all the data pretty much exactly. I mean, there's a bit of overhead for erasure coding, but not much. But you send factor of 2 more.
How is this compared? Because for turbine has this kind of separation, so that it was already a tree, right?
Turbine is a real tree,
yeah.
But the rotor, what I'm talking about here, is no tree anymore. Yeah. So you really just have one level. Turbine, in some sense, tried to be better, but was almost worse, because the more levels you have, the more faults you inject in some sense, and the more delay you have and whatnot. So this is just.
You mentioned that you were talking about that, but I'm curious because how this can be better than turbine. I mean, for me, the factor of redundancy is much bigger, and also the give was super performant. No?
It's too low or too high for you?
Too high.
Too high, too excessive. You maybe don't need that. I can give you reasons why we want that, and let me just give you a reason why we want that, apart from the fault tolerance. So we heard Itai talk about the deltas before, and people liked talking about deltas. So this is a perfect example why I don't like the deltas so much anymore. So we have a worldwide system, right? And let's say the leader sits somewhere in this world, right? Sends this data to some of those relays, and then some nodes will receive this, basically forwarded data from the relays. Now, in Itai's world, this would mean basically 2 deltas of communication overhead. And this makes perfect sense. And I think the deltas come from a time when we thought of distributed systems as being somewhat, in a room or something like that, or, somewhere maybe. So the delta was somewhat a homogeneous thing. Here, it's not so, I would say, I don't like it so much anymore, because you can think of it this way, that as a receiver, let's say if somewhere one of those 1,000 nodes, you need to have half of the relays have to send you the shred so that you can reconstruct the slice. But then if you have this over-provisioning here, then there's a chance that some relays are basically on the path from the leader to you, geographically speaking. They're kind of like, either close to the leader or close to you or somewhere in the middle, And this means there's not much overhead actually in terms of delay what you have here. So the bigger you make this over-provisioning, in some sense that costs you bandwidth, but at the same time actually saves you latency, because then you have more of these direct paths, right? You don't have to think that they always go to the other end of the world and then back to you or something like that. So that's sort of, where maybe there's a bit of a restriction when you think of deltas. So when we really are serious about this, how fast this is, I would say this takes maybe about 1.2 delta times, right? Because it's a bit more than just sending directly to somebody, but it's also not just sending to somebody on the other side of the world and then sending it back. Yeah. Okay, I'm going to make a lot of friends here. I apologize already.
So is it that the leader sends one shred to each relay? Or?
Yes, the leader sends per slice 1 shred to each relay, and then they send this shred 1,000 times out. But then for the next slice, actually, we already have different relays, so they switch very quickly. Okay, they change very quickly. Yeah. More questions? Yeah, you have the mic already.
Yeah, sorry. Are we getting the cloud providers to allow us to use multicast finally?
I mean, 00 provides this right now, right? This is kind of their business model. This is somewhat a spin-off, maybe, of what a company called Jump Trading, which is one of the big trading firms in the world. And they think this is interesting for financial applications. And so they built this, and I would say Solana is maybe their first customer where many people actually use this, sign up to this. But you can use it also for other things. But yeah, it's basically a multicast. You know, multicast is always difficult to implement because in the real internet, okay, in the public internet, you kind of have to agree on who pays the bills for multicast, right? Because you can, with one message, you can serve everybody in the world, right? That's potentially very costly, okay? And not for you, the sender, but somebody has to pay for it. And so this application sort of helps with that because people know what they're signing up for. One more.
Hey, can you elaborate a little on how the number of relays and number of shares are chosen? Does it have some like a mathematical foundational?
Not much. So there's many things you can optimize here. We didn't think so much about this. I would say we would like the number of relays a bit higher than they currently are. Currently, they're like 64. And this number comes from what Solana used before we came with the protocol. So I showed you this slide where I take everything out that they have right now. So whenever we found something we liked or didn't hate, let's put it this way, we try to keep it, okay? But these are things we can change over time. So many parameters here could be optimized. We didn't think so much about it. We want to have it out fast, I would say. Okay, let me continue. And yeah, that's basically a rotor already. So the first part is done. Let's go to voter. So this is the consensus part. So this is only at the end of a block, right? So you get all these slices now. And at the end of the block, you're going to vote on these slices. And it's basically a simplex version of the algorithm. So maybe in Solana, it works like this, that the leader would change every 4 blocks automatically, right? So there's no view change in that sense. The view change is automatic, which has some properties which are good. So many blockchains actually do that. So we have here an example. So every leader basically proposes 4 blocks. And what we're going to have is we're going to have timeouts. So these are the, we have before 3 deltas essentially. 3 capital deltas. So at some point, let's say if we had this block here, then you're going to receive the block. You're going to check real time, basically, is the block in time. And you're going to start a timer, just a local clock. There's no, nothing complicated here. Just start locally your clock counter on your PC. And you check, did the block arrive in time, essentially? Exactly like Itai explained in the general case. And we not only do this for this last block, but we do it for all the blocks, okay? So the advantage of this is even the first block here, we have a timeout that we start and we check if is it in time. The advantage is if the leader is actually currently down, which happens quite often, then we can skip and change to a new leader very quickly. So that's the advantage of doing it this way. Now, you're just going to vote, did I see the block? Basically, you vote for some block, and you say, yes, it was in time, and it was a correct block. Or you're going to say, I'm going to skip the block. It was not in time. That would be the usual case here. Or it's kind of like structurally not correct. Those are the 2 possibilities here. There could be the possibility that the leader sends you 2 blocks. We're going to get to that in a second, okay? But let's just, for the moment, assume the leader sends you a block. Okay, so then we have the votes. Let's assume everybody, the 1,000 nodes, all vote now. And as Itai said, it's an n² protocol. So what we do now is every node just sends their votes directly to every other node. Same picture that I had before. Okay, so this always means send to everybody. Okay. So let's go to the next slide. So now everybody sent the vote to everybody. Everybody receives the vote from everybody. That's the next thing you're going to do. And if the picture looks like this, so you see a lot of yes votes, basically, that the block was good. And let's say it's at least 80%. And when I say 80% here, every node actually has stake, how important they are, how much SOL they have. So some people have actually up to 3% of the whole stake. So you don't need that many votes. Some people have 0.01% of the stake, so they don't matter that much. But you need 80% of the stake to say yes. If this is the case, then you can immediately make a finalization certificate. So this is in some sense a 1-round voting protocol. You need the dissemination plus 1 round of voting. And in the lucky case, you can immediately make that. And then for you, this block is final. You can tell everybody about it. This is so-called BLS certificate, so it also fits into a single UDP block in 1500 bytes again, okay? And you send it out. You tell everybody about this, same as in simplex, okay? And, well, that could be another case, of course. This is, in some sense, the good case, and also maybe the normal case. Another case would be that it's mostly downvotes, okay? At least 60% of the stake says yes, says no. At that point, you know this block should be skipped, okay? And then you can make a skip certificate. And that's proof, again, BLS certificate, that enough people said no. And you're going to send that one out, okay? And as you can see, there's cases which are neither this nor that. There's stuff which is in the middle, right? Which kind of like mixed things here. And yeah, in the mixed case, we need one more round of voting. Okay, so this is when we need the other round of voting. We cannot finalize immediately. We have to, for instance, in one case, you could have just 60% yes votes, and that would give you enough threshold to say, let's vote now. Basically, what you call the vote first and then the decision in the end, right? That way you can make a decision certificate as well, or a finalization certificate, but a slower one. Yeah, so the whole protocol looks like this. I kept this part short on purpose. I'm not going to explain this, of course, because, and not just because I heard already that Itai is going to present this, but I would say the details here are a bit tricky, right? So you have to understand exactly when it is enough. You have to prove that. And you have to, in particular, you have to say, maybe I should explain this quickly. At some point, you're going to see more and more of those votes, but maybe it's never quite enough, so in this case, right? So maybe you never quite see these 80% that you need, you don't even see the 60%. What you're going to do, right? And at that point, you're going to say, I'm fine even with the opposite result, okay? So this is what we call fallback votes. We say, if we cannot really get to either extreme result, yes or no, then we basically vote, yeah, okay, I'm also fine with the other thing, okay? And that would help the nodes together to then say, to even construct both certificates in some sense. But you have to be careful what is allowed when, so that you don't, that you get this 20 plus 20 security. Yes?
Does this get as complex as the dollar?
No. So the question is, maybe repeat it since you didn't have a microphone. So this is, it's really very simple. I mean, it's really as simple as what you have seen here. And this is really the whole code. It's not, it's not rocket science, I would say. Yeah.
Yes. So another quick question. Can a validator be forced into a state where it must equivocate to make progress?
Can a validator have to equivocate to make progress?
Yes. Can it be forced into a state?
I mean, you would vote skip if you see a skip, or you would vote skip fallback if after some time you didn't see that you get a certificate. That's the, yes, in some sense, if you call this forced to make a skip, yes. Okay, I mean, some person wanted me to make this slide here, which kind of states a little bit what you actually can prove, okay? So we can prove.
Something that distinguishes this from Solana. So.
Yes. No, true. So what we can prove is the following, right? We can prove basically safety in the 20 plus 20 model. Safety means for us, if you have a correct node which finalizes a block in some slot, okay, slot S, and then you have another node which finalizes a block later, okay? So the slots they have numbers, okay? Slot number 1, 2, 3, and so on. So you have a later slot, and you have somebody who is correct to finalize some block in an earlier slot, then whatever you finalize here must be a descendant of the previous block, okay? So that's something we can prove. This means we cannot have forks with this protocol, assuming we have at most 20% Byzantine and 20% crash failures. And then we have liveness. So liveness is a bit more complicated, okay? So we have a simple proof for liveness, which says just with the just assuming 20%, malicious nodes, okay, just that threshold. Or it could be some crash nodes and some malicious nodes, but together it's at most 20%. So in that model, after this global stabilization time we heard before, when you have a correct leader, then the correct leader's block will be finalized. So if the network is synchronous, correct leader sends something out, we have all the timeouts that we have, then this thing will be finalized, and actually pretty fast, quickly finalized. But this is for a weaker model, as you can see here. And the problem is that if you really want to show liveness in the 20 plus 20 model, it gets quite dicey, okay, let's put it this way. Now, for theoreticians, this is nice to actually look at this exactly what happens when. But let me explain you the basic protocol. So what we have to assume here is that router works correctly, okay? So this data dissemination protocol works correctly. So this is not so trivial in practice, okay? Let me try to explain. So there's the problem that the leader could actually send out 2 blocks, okay? So it produces 2 blocks in sort of a double spend attack situation. And it sends 1 block, erasure codes 1 block and sends it to 32 of the relays, and the other block to the other half of the other 32 of the relays, okay? Now, if you think of having a situation that 32 of the relays, let's say, sit in Europe, and 32 of the relays sit in the US, for instance, okay? Then, and you have a long time between the US and Europe, okay? For some reason, this is very slow, okay? It could be asynchronous, could be super slow, okay? Then it could be that you see now these 30, you sit, let's say, in the US right now, you see the 32 block shred, for the slice for the US first, and you think that's the block, right? And I'm going to go for that. But the Europeans see another thing, and they're going to go for that. And that way you can basically produce a fork, okay? And that would be a problem. So we kind of, to deal with this here, we kind of have to assume this additional thing that this doesn't happen. We could probably enforce this in various ways, okay? So one way, for instance, would maybe not have 2x, only have 63 relays or something like that, and then you need half of them, and then maybe, it becomes difficult. But then I could argue, well, but it's still a relay, could be a bad relay, right? 20% of them could be bad. So, you have to step down a little bit, and then you have to worry about these things. So I would say practically, as a company, we don't worry about this at all, okay? But in theory, this would be, death sentence of a protocol probably, okay? So that's, just wanted to make, since I had this slide already, thanks to you, I think that's sort of the statement I want to make here.
So you're saying in practice, you're just comfortable with the 20%?
In practice, I think it will not, this is not the problem of these protocols. I would make even a stronger point somehow. So when we as distributed computing people think, or let's say, I'm a I identify as distributed computing person, even though I did rarely consensus in my life, okay? Unlike Itai, who did consensus most, maybe, in his life. But I think we are a bit too comfortable about these assumptions sometimes. So for instance, the 33% assumption, right? Bad things could happen, right? We could have more than 33% Byzantines at some point. And we should maybe think a lot more about these cases as well. And we started thinking about them, and they are truly scary, okay? So like you want to have a protocol which, fails in a graceful way, even in that case, right? And other people have also looked into this already. But that's sort of like, where I think maybe it's, if I had to find, a nice theory problem which we should study the next 10 years, I would say that's the one we should study. Because we sort of know how to do things with usual security assumptions, but as soon as we go beyond them, it's getting tricky and dicey. Yeah. There's one here. Turn it on for you.
Thanks. So one of the tricky things we have with this erasure code protocol was that we would want to have, let's say, some of the relays receiving one shred chunk, right? That was not addressed to them. And so somehow one single bad leader creating potentially all the correct chunks, but sending them to all the wrong persons. And so for that, the whole literature was simply putting a gigantic mode sending the keys as well. Are you
Okay.
also doing that somehow?
We're checking that that the shreds are correct in the end, which is not so easy, right? Because if you get a bunch of shreds, you don't want to put gigantic overhead of data into these shreds because they mostly want to send out data, and so we look into that definitely. I'm not gonna describe here probably what our solution is, but this is important stuff. Yeah. Yeah, there and there.
To the more than 33%, more than 33% of the visiting those distinction thing. To the more than 33%
Yeah.
of the malicious in the setting. So is it, can it be, prevented by somehow having introducing more nodes or looking into the economic security of the node?
Yeah, I mean, mostly we look into the case where more nodes are crashed right now, something like, or sleeping or something like that, right? So I would say that's the main thing we look into ourselves right now, because we think that's something which is very practically relevant and could actually happen. Now, if more than 33% are Byzantine, then yeah, I don't know. I mean, in our case, even just 20%, but I don't know what to say. Okay, one more, or how is the?
I would like to why? So the original Solana, people are fans here. The votes were part of the blocks, right? So they went also with Turbine, but they decided to create a new protocol voter for the votes. Why?
No. So why did we create a new voting part as well? The current thing is just inexplicably complicated, and we don't know how it works, honestly, really.
This is the accounts, the votes, the fact that the votes are transactions.
Yeah.
But, but sending out to all and thousands of nodes, how efficient really? So using relays will not be helpful.
No, the votes are also just small messages, right? As long as we don't have quantum problems, so to speak. And as long as we have small messages, this can be really done within a millisecond or so, right? Every vote. Because sending 1,000 packets is not a big problem for these beefy machines we expect, basically. So let me go to the second part, because I think I only have 30 minutes left. Okay, so this is a latency histogram. Maybe I jump over this. Just showing from a New York node basically how long it takes to do all the steps, right? That's not me. So the network is sort of the lower bound to reach everybody, but you see, depending on where they are, it can, on the right-hand side, it takes, of course, longer time to even reach a single packet to, let's say, to get to Tokyo from New York or something like that. Rotor does not add a lot of overhead to that. It is from simulations. And then we have basically, until we get 60% of the votes, in the case that we have actually the packet goes in, we have yes votes. And then we have finality, where finality here can be different things, right? It could actually be that you got 60% of the votes, at which point you would send the second round vote already, or, and then the second round vote comes in from 60% again, and then you have finality. Or you wait for more votes, and then you get to 80% of the votes, and then you have finality, or you just get a finality certificate from somebody else, right? These three things all give you finality. And surprisingly, in Solana network, for instance, in the one we simulated here, the 2 times 60%, so having 2 rounds of voting is actually often faster than having a single round of voting with 80%. And the reason for this is that a lot of stake is concentrated in a small geographic area, namely Europe. Okay, let me go to the second part. So blockchain versus NASDAQ. So I don't like these terms so much. Blockchain is fine because it's very technical, but Web3 and DLT, they're just stupid. So what we're trying to build is basically, we're trying to build a market, okay, an internet market or a capital market on the internet. So that's what I would like to have. So let's look at markets really quick. So let's assume you go to an actual market, okay, in the old sense of the world, and you need bananas, okay. And let's say you need 3 bananas for some reason. But now there's only one dude, okay, selling bananas still at the market. Nobody else has bananas, okay? And now, of course, well, I can say $130 for the 3 bananas. If you know Arrested Development, that's actually a hidden joke there. So the problem is that the market could play unfair with the users, okay? And that's something we really want to prevent, okay? And that's the idea of this constellation part. Let me quickly show you what could happen. So, we have blockchain markets, and we have problems with these. And I'm not sure whether many people are going to talk about these things this week. Is there somebody who gives a talk about these things?
Not so explicitly.
Not explicitly, okay. So let me just mention a little bit. So when you...
There's an encrypted mempool, so Bamsy will talk about it.
Okay, okay. So the problem is that if somebody sees your transaction, okay, they could do things with it, okay? They could, for instance, they could take advantage in it in some ways, okay? Let's say in particular the leader who puts together the block could take advantage by just putting a transaction which benefits them in front of your transaction. Or they could censor you right out, right? They could just say, I don't want to include this guy's transaction. So these are things we have to work with in some sense in blockchains. And this is, I would say, maybe now the main reason, this is the main reason for the next wave in some sense, as Itai put it, right? Like why some people don't want to adopt blockchains, okay? Why financial markets don't like blockchain so much. And the Nasdaq would tell you, well, we are regulated. None of these bad things happen with us, okay? So when you look a little bit, then you see many bad things actually happen with them as well. But I would say regulation helps in some sense, okay, already. So what we would like to do, and this is not just us, this is probably all of the blockchain community right now, they would like to build blockchains which don't have these issues by design, I would almost say, right? Which is even better, right? We don't need to be regulated because our protocol is so brilliant. These things don't happen anymore because we were so smart, okay? That's the idea. We don't need regulation, which would be better, right? Because here you always have to include the lawyers and do whatnot, right? It's a mess. So that's the idea. Let's quickly motivate you from another side. So what we had so far, well, we had this blockchain, as explained before, and basically every leader for every block was sort of like a little king, right? They can do whatever they want with the transactions they see. They can include them, not include them, put their own ones in. They can reorder the transactions in any way they like to make more money. That's what they do. So, yeah, that's what I just said here. So what we want is essentially no kings, okay? Yeah, so that's sort of what we try to do. So how can we get there? So a naive idea would be that we just sort of have 3 blockchains we run at the same time, okay? Not having 1 king, but we have 3 kings instead. Okay, that sounds even worse, but it's actually better, right? So we have 3 kings which just propose blocks. And we could do this by just using Alpenglow, as I just explained it before. So before you had to, see the block, and if the block was in time, you would say, yes, the block is good, and you go to the next block, basically. You vote, and you have consensus on it. So now you could think of just having a vote at the end of 3 blocks. You see 3 blocks, and you say, I've seen all these blocks. I'm happy with these blocks. Let's make a bigger block out of these 3 and move to the next block, okay? That's essentially possible. It's not without problems. So first of all, maybe it looks more like this, so bad teeth or something, right? So where maybe some leaders sometimes don't send blocks at all, and then you have to say, well, how long do I wait for the 3rd leader to send me the block before I vote? Well, I have the timeout, the Alpenglow timeout, but maybe I just see parts of it, some others see something else. It's quite messy, okay? It could even be kind of, shifted in time. If you have 3 leaders somewhere in the world, they don't adhere to the exact same time, and you have to deal with all these things. So it's not so easy. So we have many ideas how to do this, and we discussed this for almost a year now. And one idea was this idea of simultaneous release. So you have these multiple leaders, let's call them proposers, and we have this basically rotor as before, right? And what they would do here, the relays, it has to go through the relays. They would just have their timeout, like before. Rotor had just, before the the voters have a timeout, but now even maybe the relays have a timeout. They wait until some time, and they just forward whatever they got from the 3 leaders to everybody else, okay? And the idea is that this would sort of synchronize this a little bit. Maybe not all relays would agree on what they have seen from what leader in time, but maybe there would still be somewhat of a half consensus already there, and then we can have real consensus after that. That's sort of the main idea. What's negative about this is that this protocol would not be responsive in some sense, okay? Let me try to explain this. So what you would have to do here as a relay, you would have to wait until some timeout before you send the data to the next layer, okay? And this is in some sense, this waiting is bad, okay? If you have protocol waiting, that's always bad because you make the protocol much slower immediately by protocol, okay? And this is not what we want, okay? We want the responsive protocol which is always as fast as possible. You know, it doesn't have to wait for specific things to happen. That's sort of the high level idea. So, okay, so what do we do instead? So this is this constellation. On one slide of constellation, it looks honestly terrible, okay? First time you see something like this. And this is as easy as we could draw it, okay? So let me try to explain. So the second part here is just Alpenglow, okay? So I have seen this already. There's still a single leader, surprisingly, okay? We just make the leader powerless, essentially. The leader has almost no more power. Before, it could just pack whatever they wanted into a block. Now it just has to do whatever we tell him, okay? So the leader would send to the relays send to the validator. So this is the same as before. The validators only need half of what the relays send or something. So that's exactly like before. So now we have this new part at the beginning. The new part is that the users would send the transactions to so-called proposers. These are also just random nodes from the 1,000 nodes we have. They send the transactions there. The proposers would put a few transactions together, basically make slices, and send them to so-called testers, again, random nodes from our 1,000 nodes. And the testers would say, these are the slices we have seen, okay, in time, basically, and would send this to the leader. And the leader has to take their information to then produce a block, okay? So that's how we restrict the leader. Whatever the testers say this was around, the leader has to include exactly that. That's the high-level idea. I will show this picture again, but let's first understand it a bit better. Okay, so we have same thing, different view, okay? So we had the user sends to some proposer. Let's say the proposer has some transaction. Now we're going to encode the proposer. We always use the same tricks, okay? We encode this proposer's transaction into, let's say, something like shreds, okay? Maybe we use even a high, you didn't like the 2x before, this is even 4x. So this is, I have 8 of these threads here, and let's say 2 of them are sufficient to reconstruct the transaction, any 2 of them, okay? Now the proposer, it's not just one transaction. In my picture now, it's one single transaction, but it could be multiple transactions. The proposer sends these shreds to the so-called testers. Oops. They could be anywhere in the world, right? Each one gets exactly one shred. Now, the testers, what they do is they timestamp the shred, okay? So they have something like real-time information. That could be based on Alpenglow, but it could also be on actual wall clock time that they just look at the clock. And they say, I got this transaction or this whole proposal at this point of time here. And then they're going to send their shreds to the leader, which is currently in charge of putting the block together. The leader does not wait for all of them. Okay, so they are now sending this. Okay, this takes some time. The leader waits until it sees half of the shreds. At that point, it would put a proposal together with this information in. Okay, that would say this transaction was attested by these guys. It doesn't wait for the rest. Could be some Byzantine guys as well. We have to be fault tolerant at all times. But at this point here, it takes half of this half, and this is enough to reconstruct the transaction again. And it also gives the transaction a timestamp, okay? Whatever was the highest timestamp that it got here, among these 4 actually, among the 2 lower ones, that's the timestamp of the transaction. This means this transaction will basically go into that block. It's a bit different because we don't talk in blocks here anymore, but we have something even below blocks, which are called cycles, sort of like the slices of before, we have a pipelined version of this again. So this goes in here, and yeah, this transaction would then end up here. So that's sort of this view. Let's go back to this view. So this is the current numbers we're thinking about, okay? So we're actually here we think of 128 relays. Here we think we have the 1,000 validators. This is a permissionless system, so this go up and down depending on what people want. And we have really lots of attesters here, which would say, you know, these proposals came in time, and maybe something like 16 proposers, so that we have 1 in every geographic area, or something like at least, or maybe 2 in every geographic area. Yes.
How do you sample the proposals, the attesters, and the relays?
Yes, so sampling is an art by itself. The simplest thing I could say is we sample with repetition, okay? But it's more complicated than that. For instance, if you have, let's say, if you have a relay, if you have a node which has exactly 1/128 of the stake, then you might want to deterministically use that guy exactly once every time, okay?
I see.
That makes it better. And so there's actually a way to improve this.
Okay, so those are functions that are performed by your validators. Validators are not only validators, they can only be proposals, attesters, or relays, and proposals.
Yes, and chosen by randomly with repetition and some bells and whistles to make it fancy. But that actually helps a lot, so yeah.
I guess, how do you incentivize these all the other parties that
Yes, how do we incentivize these parties? So partly they get money for it in some sense, right? So the transaction pay fees. I have a slide actually for this later, but the transaction get fees, and these are redistributed among those which participate. It's a bit more complicated than that, but also that I would kind of consider an open problem, to have a protocol which really incentivizes everything. We discussed this once, and it became so complicated that it's basically, you know, at the end, if you have to pay 100x overhead to incentivize everything, and then you might start to wonder, does it make sense? But we have these things to some degree.
Somehow rationality of the timestamps that they can get. So
yeah.
explain that.
Let me show you the next slide, because it shows it a bit differently again. So we have the proposers. They send these proposals to these attesters, not just to one, but to many. And the attesters actually have, in our case now, something like a real time. Okay, think of them having a real time clock. And what they do is this real time clock is basically partitioned into 50 millisecond batches, and then the batches have numbers. Okay, and now what they would do as an attester, they just check the number I had before in my shred, was just basically telling that this was arriving in shred 17, okay, and then send it out at the end of this batch. That's what they do. Even this, I would call, this is not exactly responsive, again, because I'm waiting for something. Now you could say maybe the proposal would be smarter and send it a bit later, but you know, this has to do with geography and where they actually are, so it's not so easy to do that. But that's how you put the timestamp there.
Assume here that the province front running, because a Byzantine can put the timestamp
yes.
far in the future. Right?
Yes. The Byzantines can, of course, do all sorts of bad things, but so we can show that this is not a big problem, okay? As long as they're less than 20% again. Yeah. Good. Somehow, you know, I'm going to be very fuzzy here, but somehow this gives us somewhat a barrier, okay, for a leader being able to insert transactions which front run other transactions. Because the leader is not going to see the transactions before some time, right? This particular transaction, it's only going to see it after this time. The leader might control some of those testers, but even then they cannot puzzle it together at that point. And so this is important that they cannot now front run this specific transaction by just sending one very quickly to everybody after seeing this, essentially. This is like, I don't like this part, but that's the idea. Okay, let's put it this way. Let me show you one more thing. Then I give up.
Roger, one detail again. So is it now the case that a block is only valid if transactions are in the order of this kind of tester's timestamp? Is that what you think of?
So the block, the transactions which go into this batch essentially, they have to be in this. They have to be reported in that specific timestamp. They have to be all of 17, and then the order of them is also defined in some way. But if they get enough attestations to be able to go there, then they have to go there. The leader is going to show you what attestations they got. They cannot cheat in that sense. They can only cheat by choosing different attestations. I said the leader needs half of the attesters report something. And now, of course, they could choose one of the other half or something like that. And maybe they could move a transaction by one batch or so with that thing. But but it would be difficult for the leader to smuggle something in there.
The leader can still censor it, right?
The leader, we get to that, to censorship. Quickly this, okay, so let's say this is now all the transactions in cycle 17. Each actually, they have different lengths, so this is just how long they execute, okay? This is something the user has to provide in Solana to tell you how long is a transaction. They're going to pay for it as well. Now you could say you don't know how long my transaction executes. It depends on the if statements inside the transaction. So what you have to do is you just have to take the longest possible execution of the transaction. You're going to pay for that, even if the transaction could be very short, saying if this happened already, don't do anything. You're still going to pay the whole execution. Then there's a number in it. This is basically the fee this user is willing to pay per compute unit of this transaction, okay? So in some sense, this is a very short transaction, but each individual computation is very valuable here, whereas some are very long, and each individual, the whole thing might be more valuable than this, but then you also compute much more here. So we mostly care about this fee per compute here. And now we have to put these transactions, we have to execute them so that they are actually executable in the budget we have. So the budget looks something like this. So we have this 50 millisecond batch. This is how much we can execute. We have multiple cores which can execute things. In Solana right now we have 4. We're thinking about going to 8. So we have this parallel execution. And we basically put in the highest value transactions at the very beginning of the execution, okay? To be the first to abuse the system in some sense, what is currently available on the market. And then the lower they are paid, the less can be included. You can see here, this has a very low, very low money in it, but it's the only one which still has, is still we can still put there. There's a bunch of them which just land in the trash, okay? What I mean is they go on the chain, they go on the blockchain as well, because the leader has to show for everything they do. They cannot, hide things from you, but they will not be executed. Now, it's more complicated than that, unfortunately, because, of course, transactions could have conflicts with each other, right? Transactions could access the same accounts, for instance, and then they cannot run in parallel because then you don't know, what is the final state, right? So let's say all these big value transactions, and that actually is very realistic, okay? They all access the same accounts, okay? They all have a conflict with each other. So I cannot execute them like this, and there's some more conflicts here as well. But think of these 4 here. When you put them together, basically since they all access the same thing, they have to be executed sequentially, one after the other, okay? So first 18, because it's the most valuable one, then 12, second most valuable one, and so on. So it looks something like this. But you see, I can't do that because that would be over my compute budget at this point. So I cannot put that in, but now 8 also had a conflict. I put them on the pile here because I could not put them anywhere. But nicely 8 still fits in there, okay? So that's sort of the way to execute this. Now all the transactions which have conflicts are not executed in parallel, which is what we need here. You might wonder, for instance, 4 is now in front of 5, and it could even be that they have a conflict with each other. But we want to use these empty spaces. We want to use, this is the real bottleneck, unfortunately, okay? So we talk about bandwidth all the time, and we think of it as bottleneck, but execution is the actual bottleneck. So we now opted towards the point of view, then we say, even if 2 transactions have conflict, minor conflict, it's fine to execute one before the other, which has a lower priority, okay? So that's something we thought about, whether we should do that, and we think yes, okay? So what is important to us here is that, in some sense on a high level, that those transactions which pay a lot, okay, kind of have conflict on the most important accounts, they should be ordered correctly, but for the others we want to fill the gaps. Because if we don't do that, it could be that, think of these very high important transactions here, which all access the same account. But let's say this last transaction, after much more, this is just a toy example here. This last transaction here accesses all the accounts. That means immediately, everything else has to go out. We have no more parallelism. So, but we want parallelism. We care a lot about that. Yeah. And you see here, this high value transaction is now on the trash pile, and it doesn't have to be. So if you have such a high value transaction, then you can actually, in some sense, if the transaction wants it, you can recycle it, okay? So think of it this way. When a transaction enters the system, it tells you whether it's willing to, it has to be going into the first batch that's possible, or whether it's willing to wait a little bit more. It basically gives you a timeout, how long it's willing to wait. If this transaction here has a higher timeout, then it just goes into the next batch, because maybe it's among the most important one for the next batch. Cannot guarantee it, but that will kind of help us to reuse the block space well. Maybe some comments. So you can see, but we always will have this thing, which is, we send too many transactions onto the chain, more than we can actually execute. And we think this trade-off is worth it, because the opposite would be something like a DAG, maybe almost, where everybody has the same amount of transaction they can put on chain, and even then we kind of don't know what happens because the transactions have conflict with each other. We don't know what this would mean for execution. So we want to over-provision a little bit transactions that go on chain more than we can actually execute, so that we can execute as much as possible, because that's our bottleneck, we believe. Okay, yeah, one more otherwise, but.
Great question. So this is nice, pre-organized batch. Is that the thing that happens after the consensus, or is it the thing that is done before by the leader?
Yeah, it's a good question. So with Alpenglow, execution happens before consensus. The reason for this is that we kind of would like it that way, because then if we have a problem with execution, it goes in consensus, okay? And then we don't have consensus on something which executes differently or whatnot. However, here this is not really possible anymore. So here we need something where we have consensus, and then execution can be asynchronous, as we say, or lazy. Yeah, that's sort of what we have to deal with here. Yeah. Good, it's a complicated protocol. Let me just show you one more slide, and then and I have one for you as well again. But basically, what about paying fees, right? So I mentioned already that the transaction has something like a fee inside, and that's the thing I mentioned here, this priority fee essentially, which the transaction can choose freely. And the higher it chooses the priority fee, the more likely it actually gets executed early at the block, okay? But there's another bit we actually decided on having here, which is a fee for the proposer, okay? So the testers don't get anything particularly for them. It's also answering somewhat your question before. But the proposers get something for some reason, okay? It's almost difficult to say why, but I would say on a high level, this priority bit is somewhat the price per compute. So here we look at how much compute do we have. We have to set a price so that we don't overstrain our compute budget. Versus for inclusion, it's somewhat the price for the byte of blockchain space, which is a very different thing. And we kind of felt it deserves its own thing, okay? But you know, if one of you theoreticians tell me this is not how you should do it, I'm happy to listen. This actually goes to everybody. This goes per stake to all the nodes in the system, okay? If it's executed. And if it's not executed, which can happen, right? It can land on the pile of transactions that are not executed. Then it's just, you know, nobody gets anything. This here goes to the proposer, but only if the transaction actually is executed at the end. If it's not executed, we currently even envision to subtract this thing from the proposer. We don't want the proposer to go sub-zero. We want, you know, the 0 is the limit. But we kind of want to discourage the proposer a little bit to include a lot of spam transactions, okay? Because otherwise the proposer would just propose as much as possible, and then we would end up with a lot of transactions on chain, and that's our silly idea so far. But this is really where it gets very sketchy, okay? And it's, you know, the whole constellation is still sort of version 0.9, so it's not really done yet. But this is currently what we think of. And I have one more Tim slide at the end. So these are the things we like to prove, okay? We like to prove that there's no reordering of transactions. We like to prove that there's no censorship. And we like to prove there's no front-running sandwiching. Sort of these things that I mentioned before that we would like to have in a good blockchain. There's a bot everywhere. And it's quite easy to see it sometimes. For instance, for reordering, I already mentioned it. The leader, maybe by choosing the right, the testers has a possibility sometimes to put the transaction into the next batch, okay? That's maybe something we don't have a good solution for that. So that's sort of also reordering. For censorship as well, so the leader always has the possibility, of course, to not produce anything. There's still this bottleneck in some sense in the protocol of a leader who decides everything, right? Who says this is the block. The leader could just not do the block. How it works right now is that actually the next leader will produce exactly that batch or that block. Because the data is all there, they just have to say, this is my block now, okay? So it's kind of difficult to censor something, but it's still not impossible, because at some point you have to say, okay, now we have seen 2 hours of transactions and nobody produced any blocks, so maybe the leader is now free to choose where they start again. And also here, maybe this is the smallest spot here, but I have to prove anyway that this is happening. Good, I think I was right on time, I'm not sure, but seems to be on time. So yeah, summary, so we have these two things, right? Alpenglow and Constellation, and they're in very different states of how they're implemented. If they're both being implemented still this year, which I doubt for Constellation, okay? Alpenglow should go live this year, but Constellation might not. This is more like, you know, maybe implemented for next year. I think we have then a decent protocol with actual LaTeX specifications. Yeah, good. That's all. Thanks.
Any questions?
There you go.
So how do we capture between transaction dependencies? So we depend the leader
Who understands what are the dependencies? Between transactions. So in Solana, this is already true now. So Solana, in some sense, has done a few things right, and execution was something they did well, I would say, in the past. And they already, at the beginning, as a user, you have to specify what accounts you're going to touch, potentially. And that's how we figure out what are the possible conflicts that we're going to have. Read and write and all these things, yeah. So this is already done in the system that's running right now. this is, I would say, the main reason why we have so many transactions per second that we can support, because we have this parallelism even right now, and that we don't have to change anything for that.
So with this new consultation, you still have 4 slots to propose?
No, actually that will change very soon, that we have the 4 slots per proposer. People think now to have less slots per proposer. Even now this is helpful somehow, because the more slots you have as a proposer, the more power you have. So we'd like to make the slots shorter, we'd like to make fewer slots per proposer. So now they think about 2 slots, which only are half the time as they are right now. And so, you know, Constellation being so far out for the parameters, actually, first of all, I would say this is above my pay grade, so I never decide the parameters. I put some parameters into the white papers, but then some CEO guy comes and decides this.
I think you agree that you increase the censorship by making more, so the more of censorship
not anymore with Constellation, because the leader is so much tied down what they can do. I think for that it would be not a big problem to have that. And actually go back to even the view change world, where we say the leader produces now as many blocks as they want, and then at some point, you know, people say, we are fed up with this leader, let's do a change, right? Just skip, and then we have a new leader. We could do that, and it would have its advantages as well, because a leader change is somewhat expensive, because you have to have a bit more timeouts.
So you're helping me.
Yeah.
I think on Solana, upwards of like 60 or 70% of the value is from outside client.
Yeah.
I'm curious with Constellation, do you expect proposers to basically because they already on the software that development? So I guess my question is like a lot of complexity. Is it actually doing anything, or will like a company basically just hide complexity and simply give a single?
True. So I would say true. Many run, clients which are modified right now. The reason for it is a bit profane, right? It's just that they, for instance, have a problem that many transactions are junk transactions, and they want to filter those, and then they run these modified clients to have that. There could be collusion is always a problem, but in some sense, this is where I would say our usual model assumptions should kick in. So if you really collude to do something very bad, then you would be considered Byzantine. And for Alpenglow, we have measures, I would say, in the background, how we just measure what our node's doing, and we probably would see this quite quickly. And we don't have automatic punishment right now. We don't even plan to have that, but if this becomes a problem, we would take it very seriously. And of course, we try to define and design our protocols so that it's not so easy. Yeah. One more.
It reminds me of I think if you kind of keep line like block works as like an opportunity, feels like an opportunity for like a shading force.
Yeah. No, I know. Yeah, many problems still to come. Cool. Thanks again.
Let's thank Roger again.